Hey everyone, welcome back to the channel. Today we are diving into one of the best GPU performance blog ever written. How to make simple CUDA matrix multiplication kernel and optimize it all the way to almost CUBLA's level of speed. Don't worry, I'm going to explain everything in simple language. Even if you are a beginner or somebody really new to CUDA, this video is going to make you think like a GPU engineer. This entire walkthrough is inspired by Simon Boehm's CUDA matrix multiplication workload, and trust me, it's pure gold. So before we get started, we might need to know why matrix multiplication matters. So why do we even care about matrix multiplication? In deep learning, matrix multiply is literally everywhere. Transformers, MatMul, CNNs, MatMul, training, MatMul, inference, MatMul. More than 90% of compute inside the large AI models is just matrix multiplication. So if you want to optimize a model, you can automatically understand how GPU thinks and how they move the memory and how to squeeze the performance out of hardware. And Simon Boehm does it in an incredible good way by introducing naive CUDA multiplication code and optimize it all the way to a really good standard where you get almost 93% of CUBLA's level, which is an NVIDIA library itself. So in stage 1, Simon Boehm introduced a naive matrix multiplication where it reads all the full row from matrix A and full column from matrix B directly from the slow global memory, and guess what? It is incredibly slow. The performance is around 1.3% of CUBLA's, and that's basically the GPU saying, bro, this is not how you use me. Do you know why that is really slow? That is because the data or the threads access the global memory, and the data is scattered around the space and it's not continuously arranged. Then GPU streaming becomes really small and it becomes reading the memory in a very inefficient pattern, and every load has to come from memory over and over again, making it really slow. For example, here this is an example of naive multiplication between both A and B, and you can see that both the columns of B is loaded from same both the threads loads the same column to multiply two rows of A. That means that even for row 0 and row 1, you have to load the same column 0 to multiple times to meet the requirement, like row 1 dot column 0, row 2 dot column 0. So that takes multiple time if you have lots of memory or lot of operations to do. Moving on, then he suggested some improvement. First one is memory coalescing. So in memory coalescing, what happens is that to fix the slow memory access, the first big optimization is called memory coalescing. This simply means that threads in a warp should read memory that is next to each other. Imagine 32 students in a line. We have asked them to collect 30 random books from different parts of the library. It's going to be slow because these children are going to run around trying to fetch their best books or favorite books. But now imagine all the 32 students asking for the books from the same shelf in an order. It will be much faster for us. We just go to a single shelf and collect all the books together. We can even collect all the books together, and this simple trick can boost the performance from 309 gigaflops to 1986 gigaflops, and that is almost like 6 times the naive speed. For example, this is how the memory is accessed when the memory access is consecutive, and this is how it looks when it is like really random. Moving on, the third mechanism what he introduced was shared memory. So the next thing we just introduce to our methodology is GPU superpower, the shared memory. Shared memory is like a tiny cupboard inside each streaming multiprocessor. It's extremely fast. instead of reading from the same values from a global memory again and again, we load small tiles of matrix A and B into shared memory. Now, threads can reuse the data multiple times. This increases the performance to around 2980 gigaflops, and you can literally feel the GPU say, finally you are using me properly. And as you can see, this is like really fast because previously we used to run around between the DRAM and static memory. Now we are using the memory that is already the on-chip memory, and it is almost like 6 times faster, and the cache is really faster than getting the data from DRAM. So that's the another method that we use. Then there is the thread level tiling. Instead of instead of just thread doing just one output element, we give each thread a tile, a small block of output. This increases something called arithmetic intensity. That means more math for every byte of memory loaded. With 1D tiling, performance jumped to 8474 gigaflops. Then we move to 2D tiling, both height and width, and the performance jumps around to 15,000 gigaflops. We also add vectorized memory loads like loading float 4 instead of float 16, and that is to reduce the precision and improve the speed of compute. The performance when we do that precision reduction, the performance again rises to 18,000 gigaflops. And now you can see why GPU programming feels like a game of how do I reuse this data more efficiently. Then we use warp tiling and auto tuning. So the final layer of optimization is warp tiling. This means we design the kernel so that work around tiles together. This uses the registers more efficiently and reduces the synchronization. And then comes the magic word auto tuning. We try different tile sizes, block sizes, and vector widths automatically. This pushes the performance to 21,000 gigaflops, and that is 93% of CUDA. Squeezing out the last 5-10% is really hard, but getting to the 90% is very achievable, and with these techniques. So what we have learned over this time is lesson 1: access the memory in a coalesced way, that get the memory from the continuous memory space, which improves the speed. Then use shared memory to reuse the data, give each thread more work, use vector loads where possible, and tune, profile, and experiment. These ideas apply not to just MatMul but to any GPU kernel. If you want to think like a GPU engineer, these are the concepts that you should master. And that's the full journey from slow naive kernel all the way to CUDA's performance. If you want to follow up where I write a CUDA kernel live and optimize it step by step, tell me in the comments. And thanks for watching. I will see you in the next video. Bye.